Good morning. Today I am going to deal with the basicity of amines. Why amines are basic? We know that all the kinds of amines like ammonia contain lone pair of electrons on nitrogen atom. So they have a tendency to donate its lone pair of electrons towards an electron deficient species. Then it can act as a base. Here, this is our ammonia. When this lone pair of electrons donates to a proton, it will convert it into a protonated ammonia. That is our NH4 plus ammonium. And this is our primary amine RNH2. When the lone pair of electrons present in nitrogen donates electron to the proton, it will convert it into protonated cation, that is RNH3 plus. And this is our secondary amine. When this secondary amine protonated, it will convert it into R2NH2 plus. And this is our tertiary amine. When it is getting protonated, it will convert it into R3NH plus. The basicity order of amines in aqueous medium is determined by three factors. One is plus I effect of the alkyl groups. Second factor is extent of hydration of the amine cation, or it is called a solvation of the protonated amine. Then third factor is steric hindrance of the alkyl groups. Then what is the effect of plus I effect in primary, secondary and tertiary amines? We know that what is plus I effect? That is electron donating inductive effect. So in aliphatic amines, the plus I effect of the alkyl groups increases the electron availability on the nitrogen atom, and it makes them more basic than ammonia. So what will be the order of basicity? Tertiary amines will be more basic than secondary amine, and which will be more basic than primary amine, and which will be more basic than ammonia, due to the presence of three electron donating substituents in tertiary amine, two electron donating substituents in secondary amine, and one electron donating substituent in primary amine. The next factor is extent of hydration of the protonated amine. What is the formula of protonated amine in all the three amines? Here, this is the protonated amine of primary amine, that is RNH2. When it is getting protonated, it will convert it into RNH3 plus. This is R2NH2 plus, that is the protonated amine of secondary amine, and R3NH plus, that is the protonated amine of tertiary amine. How can you determine the extent of hydration of these protonated amines? As the number of hydrogen atom increases, it will be more stabilized by hydrogen bonding, and it will be more stable protonated amine. So the extent of hydration will be more in the case of primary amine, which will be more hydrated protonated amine due to the presence of 3 hydrogen atoms in this cation. And secondary amine will be less hydrated due to the number of hydrogen atom present in this secondary amine is 2. And tertiary, in the case of tertiary amine, the number of hydrogen atom is 1. So the hydrogen bonding will be less for tertiary amine. So the order of extent of hydration or extent of solvation is primary greater than secondary, which is greater than tertiary. Then this hydrogen bonding factor or hydration factor favors a basicity order. So what will be the order of basicity? Primary will be more basic than secondary, which will be more basic than tertiary. Another factor is steric hindrance of the alkyl groups, which will be more sterically hindered to the availability of lone pair of electrons on the nitrogen, which will be more sterically hindered amine. That is, tertiary will be more sterically hindered amine. So tertiary will be less basic than secondary, and which will be less than primary. And this steric hindrance factor tends to decrease the basicity of the amine. Then what will be the order of basicity of amines? Primary will be more basic than secondary, which will be more basic than tertiary. Let us discuss the basicity of methylamine, dimethylamine and trimethylamine. All the 3 amines are more basic than our ammonia due to the plus I effect of the methyl group. Plus I effect will increase the electron density on the nitrogen atom of the amine. Then what is the case of dimethylamine? Here there is 2 methyl groups, that is 2 plus I effect substituents. Hence the electron density on nitrogen atom will be greater than our methylamine. This will favors greater basicity of the dimethylamine. But here there is less solvation effect due to the number of hydrogen atoms, or hydrogen bonding will be less in the case of dimethylamine compared to our methylamine. This is protonated dimethylamine. This is protonated methylamine. Here the number of hydrogen atoms is 3 and here the number of hydrogen atom is 2. So hydration factor is more in the case of methylamine than our dimethylamine. And what is the effect of steric factor? Steric factor is more in the case of secondary amine than primary amine. So, which will be more basic in the case of steric factor. In the case of steric factor, primary amine will be more basic than our secondary amine. However, here plus side effects outweighs the combined hydration factor and steric factor. So, which will be more basic? Dimethylamine will be more basic than our methylamine. Then consider the case of trimethylamine. This is the structure of trimethylamine and this is the structure of protonated trimethylamine. Here there is 3 electron donating substituents. So plus I effect is more. Then basicity is more for tertiary amine. Then what about the hydration factor and steric factor? This is the protonated amine. Here number of hydrogen atom is 1. Then hydration factor will be less. So basicity will be less in the case of hydration factor. Then what is the effect of steric factor? Here steric hindrance is more in the case of tertiary amine. It will decrease the basicity of tertiary amine. Then what is the predominant effect in the out of all the 3 effects? In the case of trimethylamine, the combined hydration factor and steric factor outweighs plus I effects, which means trimethylamine is less basic than our dimethylamine and it is found to be less basic than even our methylamine. Then what will be the order of basicity? Dimethylamine is more basic than our methylamine and which will be more basic than trimethylamine and which will be more basic than our ammonia. Next example is the basicity of ethylamine, diethylamine and triethylamine. Obviously, all the 3 amines are more basic than our ammonia due to the plus I effect of the ethyl groups. It will increases the electron density on nitrogen atom and it also increases the basicity. Then what is the case of diethylamine? In the case of diethylamine, there are 2 electron donating substituents. 2 plus I effect substituents are present. So electron density on nitrogen atom will be greater than our ethylamine. And this will favors the basicity of diethylamine. However, there is less stabilization of cation from hydrogen bonding and greater steric hindrance from its ethyl groups than our primary ethyl amine. So both the combined effect of hydration factor and steric factor will be less predominant and plus I effect outweighs these 2 factors and which will be more basic. Diethylamine will be more basic than our ethylamine. Then what is the case of triethylamine? Here there is 3 electron donating substituents and this is the structure of protonated tertiary amine. So the electron density will increase on nitrogen atom. It will facilitate the basicity of amine. Whereas the stabilization or hydration factor and steric hindrance will inverse the basicity of the tertiary amine. Then the net result of these three effects, the tertiary amine or triethyl amine is less basic than our diethyl amine, but it is more basic than ethyl amine. Then what will be the order of basicity of ethyl amines? Secondary amine, that is our diethyl amine, is more basic than triethyl amine, and which will be more basic than our ethyl amine, and which will be more basic than our ammonia. Next we have to discuss about the basicity of aromatic amines. Generally all the aromatic amines are less basic than not only our aliphatic amines but also ammonia. And what will be the reason for the less basicity of our aromatic amines? This is aniline, an aromatic amine, which is less basic than aliphatic amines. Why? NH2 group have plus M effect, that is electron donating substituent, that is electron donates to the ring, that is plus M effect. Then what will be the resonance structures of aniline? Here the lone pair of electrons will donates to this bond and this bond will shifts to this carbon. We get this structure, and this negative charge will shifts to this bond and this bond will shifts to this carbon. Here the lone pair of electron donates to the ring, so nitrogen getting positively charged. So the availability of lone pair of electrons on nitrogen atom will decreases due to the resonance effect. So the aniline is less basic than ammonia or aliphatic amines. Here the electron density on nitrogen atom will be less. Further, the protonated aniline, that is called anilinium ion. Anilinium ion has only two resonance structures. So it is not stabilized. So aniline has less tendency to donate its lone pair of electrons towards proton. Then what is the effect of substituents on the basicity of aromatic amines? First we have to discuss about the effect of substituents on the nitrogen atom. First, in the case of electron donating substituents on nitrogen atom, compare the basicity of aniline, N-methyl aniline and N-dimethyl aniline, which will be more basic. Here the electron donating substituents will enhance the electron density on nitrogen atom, then which will be more basic. Obviously N-dimethyl aniline will be more basic than N-methyl aniline and which will be more basic than our aniline. Then what is the effect of electron withdrawing substituents on nitrogen? Here there is two C6H5 groups, two phenyl groups, and here there is three phenyl groups. So the electron density on nitrogen will decrease due to the resonance stabilized structure of diphenylamine and triphenylamine. Then what will be which will be the more basic amine? Obviously, aniline will be the more basic than our diphenylamine, and which will be more basic than triphenylamine due to the availability of lone pair of electrons present in nitrogen will be very less in the case of this tertiary amine. Next is the effect of nuclear substituents. Here we have two different types of nuclear substituents. One is electron donating groups, another one is electron withdrawing groups. Which type of substituents will facilitate the electron density on nitrogen atom? Of course, electron donating substituents will facilitate the basicity of aromatic amines. So, the substituents, electron donating substituted aromatic amines will be more basic than electron withdrawing aromatic amines. That is the general thing about the basicity of aromatic amines. Then another general effect is ortho effect. What is ortho effect? An ortho substituted aniline is a weaker base than aniline, irrespective of the electron donating or electron withdrawing nature of the substituent group. This is known as ortho effect, and this ortho effect is due to the combined effect of electronic and steric effects. So, according to ortho effect, it doesn't depend on the nuclear substituent is electron withdrawing or electron donating. Irrespective of the substituent, ortho substituent will be weaker base, that is ortho effect. And the reason of ortho effect is combined electronic and steric factor. So, ortho amino aniline will be less basic than meta, and which will be less basic than para aniline. And here NH2 group is plus M effect substituent. Another case is of orthochloroaniline, or orthochloroaniline will be less basic than meta and parachloroanilines. All this effect is due to ortho effect. Another generalization is the base strengthening effect of an electron donating group will be takes place at the para substituent, which means if the electron donating substituent present at para position, its basicity will be more than our meta substituent. Consider an example of para-anisidine and meta-anisidine, which will be more basic. Here OCH3 group having plus M effect. So, the electron donating group, here the basicity will be enhanced when the electron donating substituent present at para position compared to meta position. Why para-anisdine is more basic than meta-anisdine? Let us discuss its resonance structures. Here, OCH3 group will donate lone pair of electrons from oxygen to this bond, and this bond will shift to this carbon and it will converted into this structure, and lone pair of electron lost for oxygen and getting positively charged, and this negative charge will shift to this bond and this double bond will shift to this carbon, and here negative charge will concentrated on the carbon at which NH2 group is attached. And these are the resonance structures of para-anisdine. And why it is more basic? Here, the negative group is attached with the negative charge is attached with the carbon, and which is attached with the NH2 group. So, the electron availability will be more in the case of para substituent. Whereas, compare the resonance structures with the meta-anisdine. Here, the lone pair of electron donates to this bond and this double bond will shift to this carbon and we get this structure. Lone pair of electron lost for oxygen and getting positively charged, and this negative charge will shift to this carbon and this double bond will shift to this carbon and getting this resonance structure. And here there is no negative charge concentrated at the carbon at which NH2 group is attached. That's why meta-anisdine is less basic than our para-anisdine. Then what about electron withdrawing group present at para position? If the electron withdrawing substituent present at para position, it will be less basic than meta position. That is, base weakening effect will happen when electron withdrawing substituent present at para position. That's why meta-nitroaniline is more basic than our para-nitroaniline, which can be explained on the basis of resonance structures. These are the resonance structures of para-nitroaniline. Here the lone pair of NO2 group is an electron withdrawing substituent. So the lone pair of electron present in nitrogen withdraws from nitrogen to the substituent, that is minus M effect. So the electrons shifts to this bond and this bond will shifts to carbon and nitrogen getting positively charged, and this negative charge will shifts to this bond and this double bond will shifts to this carbon, and the negative charge again shifts to nitro group, and these are the resonance structures. Here, the negative charge is concentrated on the carbon at which NO2 group is attached. So, the para-nitroaniline will be less basic. Then, what are the resonance structures of meta-nitroaniline? Here, NH2 group lone pair of electron donates to this bond and this bond will shift to this carbon. A negative charge will shift to this bond and this bond will shift to this carbon, and these are the resonance structures. And here there is no negative charge on the carbon at which NO2 group is attached. That's why meta-nitroaniline is more basic than para-nitroaniline. In the case of para-nitroaniline, The negative charge is concentrated on the carbon at which NO2 group is attached. As NO2 group withdraws electron density, it will cause decrease in electron density on the nitrogen atom of the NH2 group and decrease in the basicity of amine. That's all about the basicity of aliphatic amines and aromatic amines. Hope it is clear. Thank you.